All right, today we're going to dive into the hidden world of organic chemistry. We're going to see how just a few simple rules and one really key element build literally everything around us, from the fuel in our cars all the way to our own DNA. So let's jump right in. Okay, so let's start with a little bit of a puzzle. What could possibly connect the plastic bottle you've got on your desk, the aspirin in your medicine cabinet, and the gasoline that powers your car? I mean, they seem completely different, right? Well, it turns out the answer lies with one single, pretty extraordinary element. And that element is carbon. Yep, plastics, medicine, fuel, they're all carbon compounds. And that, right there, is the heart of organic chemistry. So what makes carbon so special? Well, it's a master connector. It has 4 available spots for bonding, which means it can build these incredibly strong, stable chains, rings, and super complex structures in a way that pretty much no other element can. I want you to think of carbon as the ultimate Lego brick. Seriously, with just this one type of piece, you can build an entire molecular world. So let's start with the most basic blueprint there is. So, say hello to the alkanes. These are the simplest family in all of organic chemistry. They're made of just carbon and hydrogen atoms, all connected by simple, single bonds. And because they're packed with as many hydrogen atoms as they can possibly hold, we call them saturated. These are the straight, chain, no-frills foundations of the whole field. Now, check this out. Watch how one tiny change creates a world of difference. If we just swap out a single bond for a double bond, boom, we've created a whole new family called alkenes. If we take it up a notch to a triple bond, you get alkynes. By doing this, we go from saturated to unsaturated, which just means the molecules now have some room to react. This simple change in connection, it unlocks entirely new chemical possibilities. It's like creating brand new Lego bricks that have totally different ways of connecting to each other. So, with these new types of bonds in our arsenal, our molecular toolkit gets a major upgrade. We're officially moving beyond simple chains and into more complex, more reactive structures. So, what's next? Well, what happens when carbon decides not to make a chain, but to form a loop? Carbon doesn't just form chains. It can also loop back on itself and form rings. And the absolute king of these rings is a molecule called benzene. It's a 6-carbon ring that has this really unique alternating pattern of double bonds, and this structure is incredibly stable. It actually forms the structural backbone for a huge number of really important substances. And when I say important, I mean it. This simple ring is a chemical superstar. It's the core of painkillers like aspirin and ibuprofen. It's the starting point for making dyes and plastics. It's used to boost the octane in our gasoline. It even forms the backbone of an explosive like TNT. It's honestly incredible to think how one stable shape can lead to such a massive range of uses. So far, we've seen how changing the types of bonds and the overall shape can change a molecule. But what happens if we use the exact same atoms, but just, arrange them differently? This brings us to a really fascinating concept in chemistry. We're talking about isomers. Now, the crucial thing to get here is that isomers have the exact same molecular formula, the same number and types of atoms, but a different structural arrangement. The best way to think about it is this. You've got the same ingredients, but you follow a different recipe. And the result? A completely different dish. Let's look at a classic example. C4H10. Okay, so we can arrange these atoms into a simple straight chain. That's called butane, which you'd find in a lighter. Or we can rearrange them into a branch structure called isobutane, which is used as a refrigerant. See? Same parts, but the different shape gives them entirely different jobs to do. But the subtlety doesn't even stop there. Those rigid double bonds we saw earlier, they create another kind of isomer. If the main parts of the molecule are on the same side of that bond, it's called cis, and it creates this kind of kinked U shape. If they're on opposite sides, it's called trans, which makes it more straight and linear. So why does this matter? Well, think about fats. That cis kink prevents molecules from packing together tightly, which creates oils that are liquid at room temperature. But the linear trans shape packs together really easily, creating solid fats. A tiny change in geometry makes all the difference in the world. Okay, we've seen how to build and rearrange small molecules. Now, let's scale things up, way up. What happens when we start linking these small units together into massive chains? This is how we assemble the molecular giants that really define our modern world. And now, we enter the world of polymers. A polymer is just a very, very long molecule that's made by linking together lots of small repeating units called monomers.
The absolute best analogy for this is a chain of paper clips. Each individual paper clip is a monomer, and the entire chain, all linked together, is the polymer. Simple as that. So how do we actually forge one of these polymer chains, like the one in a plastic bag? Well, it's basically a three-step process. First up is initiation. We introduce an unstable molecule called a free radical. You can think of it like a chemical spark, and it attacks a monomer's double bond, breaking it open to get the chain started. Then comes propagation. That newly opened bond is now super reactive, so it grabs another monomer, which then grabs another, and the chain starts to grow incredibly fast. And finally, you have termination. The whole reaction stops when two of these growing chains find each other and combine their ends, creating the final stable polymer. Now, that process we just talked about is called addition polymerization, where monomers just add on to each other, clean and simple. But there's another way called condensation polymerization. In this case, two monomers join together by kicking out a small molecule, usually a molecule of water. This is the process that creates materials we know, like nylon. And what's really fascinating is it's the very same process that nature uses to build the proteins in your own body. And that brings us to a final, really crucial comparison. You see, we've become masters at building our own polymers in labs. But let's be honest, nature has been doing it for billions of years. So let's take a look at the world we've built versus the world that built us. So on one hand, you've got nature's polymers. Things like DNA, proteins, silk. They're all created through these elegant biological processes inside living things. On the other hand, you have our synthetic creations, plastic, nylon, silicone, all born in chemical labs. But here's the crucial difference, and it's a difference that defines one of our biggest modern challenges. Nature builds its polymers to be recycled. They're biodegradable. Our synthetic polymers, well, for the most part, they're built to last forever. So let's pull all this together. We started with a single element, carbon, our ultimate Lego brick. We saw how simple changes, going from single to double bonds, from chains to rings, creates this vast and incredibly diverse molecular world. We discovered that even with the exact same atoms, just a different arrangement creates isomers with totally new functions. And finally, we saw how linking these little pieces into giant polymer chains builds the very fabric of our modern lives, from the DNA inside us to the plastics we use every single day. And this really leaves us with a final inspiring thought. Carbon is the element of life, but it's also the element of innovation. It has built the simple alkanes we burn for fuel, and it has built the unbelievably complex double helix of our DNA. So the question is, as we get better and better at understanding and manipulating these molecules, what incredible new materials, medicines, and technologies will carbon allow us to build next?